In this video, we will discuss constant coefficient homogeneous second order linear differential equations. But before that, we need to go over two things that well, they do pertain to that, but they are prerequisites, if you will. You can skip them if you would like. I'll include a timestamp. First thing we need to go over is a quick review of linear algebra, and more specifically linear combinations. So this will seem a little bit out of the blue maybe right now, but just continue watching and it'll start making sense soon. So in linear algebra, when you guys looked at linear combinations, you were introduced to something like this, right? So you had an xy plane, and they gave you two different points, right? So this just for making it easy, let's just pick 1, 0 and 0, 1, right? And then what you did was you would basically, in order to span the entire vector space R2, you would have to have two vectors, and these two vectors could span R2 as long as they were not the zero vector and they were not scalar multiples of each other. So let me write that down. So in order to span R2, so in order to basically map out the entirety of the two-dimensional plane, you need two vectors which are not the zero vector and are not scalar multiples of each other. And the way of finding out if two coordinates were scalar multiples of each other was the determinant, right? Was the determinant. But I'm not going to go into that. Basically, that's the entire notion. So if, for example, let's say we had two different points here, and these 2 points were scalar multiples because they were on the same line, right? Then they could only span this line, right? These two vectors. However, because these two vectors are not scalar multiples of each other and are not the zero vector, then and the zero vector is just 0, 0. That's just a fancy way of writing 0, 0. Maybe I'll highlight that. Okay. So these two vectors are not scalar multiples of each other, and so you can multiply both of these vectors by different numbers, and you could come up with any vector, and you could come up with any vector. So you could come up with this vector, you could come up with this vector, you could come up with this vector, and it could be of really great length, it could be a very short length, right? You could come up with an infinite amount of vectors, and all of these vectors would sum up and give you the vector space R2. That was the concept, the general concept, right? So based on that, we could write something like R2 is equivalent to C1 0, 1 plus C2 1, 0 such that C1 and C2 are elements of real values. So C1 and C2, they're just constants, and they can be any constant in the real set. Okay, so that's basically the notion of a linear combination. So that this is very important, this thing right here, because this idea of combining two vectors and then having two parameters, C1 and C2, that you can change, that are just numbers, scalar numbers, are going to come in very handy when we start talking about second order linear differential equations. Okay, so then this was the first concept that I wanted to talk to you about. The second concept that I want to talk to you about before we delve deep into second order linear differential equations is the Wronskian. Okay, so the Wronskian is a method of determining a fundamental set of solutions given y1 and y2. So you could think of y1 and y2 as the vectors here. Okay? You could think of y1 and y2 as those vectors. And so these two vectors, they had these conditions, right? They could not be the zero vector, and they could not be scalar multiples of each other. And so the Wronskian checks all that. So basically, if I should change my color actually. So if y1 and y2 don't satisfy the equation, and I'll show you what the equation is. Don't satisfy the equation. Then come on, y1 and y2 are not a fundamental set of solutions. Okay? So they're not a fundamental set of solutions. So this is like saying, let me show you the equation first. I need to stop delaying that. So the equation of the Wronskian is as follows. So Wronskian, and then you have curly bracket y1, y2, and then you take the determinant of y1 and y2, y1 prime, y2 prime. And this is I'm drawing parallels with linear combinations, because in order to determine whether or not you have scalar multiples of each other, you would take a determinant, right? And this is the same thing. However, we're not doing it with like scalar values, like numbers. We're doing it with equations now. So y1, y2 prime minus y1 prime, y2. And this cannot equal 0. And as long as it does not equal 0, this is the condition that is required to form a fundamental set of solutions. Okay? So again, if, okay, let me write this down again. Okay, if this thing does end up equaling 0, then this doesn't form a fundamental set. And I'm just going to write FS, fundamental set. Okay, fundamental set. So that means that it's not, that y1 and y2 are not linearly independent. Okay? So that's the Wronskian. So that's basically it. This was required. I needed to show you what the Wronskian is and what it means, because when we go into second order linear differential equations, I'm going to need to use the Wronskian almost like a pseudo proof to show you like one case. Okay? So with that in mind, now we can finally introduce to you what a second order linear differential equation is. So a second order linear ordinary differential equation looks like this. This is the general form, and this will look, and the format in which I'm going to write this is very similar to when I first introduced the first order linear differential equation. So the general form is a2t y double prime t plus a1t y prime t plus a naught t yt equals bt. And I should also note that a2t must not equal 0. Otherwise, then you'll get a first order linear differential equation. Okay, so then now with that in mind, we can continue, and I can say I can divide everything by a2t, and that will basically yield this. That will give me a standard form. And the standard form is basically where you've divided up everything by a2t, and you've just assigned, instead of having fractions like ugly fractions where you have a1t over a2t, you've just assigned these ugly fractions to be some variable p, and same thing with a naught t. So a naught t over a2t equals qt, and bt over a2t equals gt. Okay, so these are the three that you need to know, and I will choose a different color. Let's go with pink. So the standard form therefore is y prime t plus pt y prime t plus qt yt equals gt. That is your standard form. Also note, and this is more just for the sake of completeness, note that we are assuming that p, q, and g are continuous functions. Okay, so we're assuming that p, q, and g are continuous functions. All right. Yeah. Now we are only going to be in this video dealing with the homogeneous case. So we are only going to be dealing with when gt equals 0. We are only dealing with GT equals 0 in this video. This is important. Okay, so first it's important to know how to solve the homogeneous differential equation, and then we can, once we know how to do that, then we will go and solve the non-homogeneous case. Okay, this GT equals 0 is the homogeneous case, just for the record, homogeneous. Okay, and then when GT does not equal 0, this is the non-homogeneous case. Okay, so two different cases, you got to know the difference. Okay, so we're only dealing with when GT equals 0. So we are only in this video dealing with, we're only dealing with this equal to 0. Okay, maybe I should make that pink. Then I can make this white. All right, so cool. This is what we're dealing with. Excellent. Now, I need to show you a few things. So we're going to, so first things first, we will be dealing with the constant coefficient case as well. Okay, so this is there's going to be times when PT and QT are in terms of T, but we're assuming that P and Q, for this case, are just going to be constants. So I'm going to rewrite this equation as A y prime t plus B y prime t plus C yt equals 0. So this is constant coefficient case. There's a case when it is not constant, and then you cannot solve the equation like how I will solve it here. But yeah, so just know that. So in the future, we will deal with the case where you have P and Q, which are in terms of T, and they're not just constants, there's some actual value. But just for the sake of this video, just to introduce you to second order linear differential equations, it's just going to be A, B, and C. Okay? So when it's A, B, and C, it's much simpler. And what we can do is we're going to guess a solution. Okay? We're going to guess a solution. Okay? And based on this guess, we're going to derive some things. So we're going to guess a solution. Guessing a trial solution. We're going to guess a solution. So the solution we're going to guess is ERT. Okay? Where for all, this means for all, by the way. But anyways, for all R is an element of the reals. Okay? So R is a constant. That's what I'm trying to say. So R is going to be some constant, but we don't know what it is. Okay? So given that yt, I'm just going to rewrite this, is e to the rt. Y prime t is re to the rt. Y double prime t is r squared e to the rt. And so if we plug these in to this equation right here, we can solve and find the value of r. So let's plug that in. So a, we have a, and then we have this r, this double prime. Okay, and then we have b, and then we have this y prime t, and then we have c, and and then we just have yt like so, and this equals 0. All right, and so now you can see that in each of these terms there's e to the rt, so we can bring that out. So e to the rt ar squared plus br plus c equals 0. Okay, and so based on this, let me bring this down actually. Oh sheesh, let me bring that out down here. All right, so now look, e to the rt, whatever r is, r we know is just some constant. So r can be positive or it could be negative. We don't know, but it doesn't matter because on the xy, or yeah, okay, so like if on the, I was going to say on the xy plane, but I notice it's in terms of t. But we can just say t and then f of t, okay, where f of t is defined as e to the rt. Sure. And so whatever r is, it's going to look something like this, right? Where you have some exponential function and it's going to look something like that. But you don't know what it is because we don't know if r is positive or negative. So as a result, what's going to happen is, at least we can tell that this e to the rt is never actually 0. So that means that this is never 0, right? So that means that this is all we need to worry about, right? Because ar squared plus br plus c can equal 0. And in fact, this is going to lead to 3 different cases. We're going to have to deal with 3 different cases. So, and that's because of the quadratic formula. So recall that we're going to have to use the quadratic formula to solve this. So remember the quadratic formula is r equals minus b plus minus b squared minus 4ac in a radical over 2a. So that's your r. Now we're here, and what we need to do is we need to think about 3 different cases. So this radical is a pain in the ass. That's just how it is. Okay, it really is a pain. So therefore, we're going to have 3 different cases based on the radical. We're going to have a case where b squared minus 4ac is greater than 0. We're going to have a case where I'm going to call this A, I'm going to call this B, case B, and case capital C, where b squared minus 4ac equals 0, and then b squared minus 4ac is less than 0. We're going to have these 3 cases. And the thing is, each different case is going to have a different thing going on. So with this, you're going to have 2 real roots. 2 real distinct roots. Okay? Distinct is an important distinction. 2 real distinct roots. And then with this, when you just have 0, then this whole thing goes away, and you're just left with minus b over 2a. And I'll go into this in much more detail, but I'm just trying to give you like a rough intuition. This will give you 1 real root, and this will give you 2 complex roots. So yes, we do have to deal with complex numbers. It kind of sucks, but it's not too bad. And so now that we have that in mind, we're going to begin looking at the first case. So the first case is case A, right? So let's look at case A. So case A, and I should probably change my color. Case A Case A is when b squared minus 4ac is greater than 0. Okay, well, in that case, you're going to have R1, which is minus b plus minus b, and then I should just write 2a, plus b squared minus 4ac over 2a. And then you're going to have R2, which is minus b over 2a minus b squared minus 4ac over 2a. And so those are your two different distinct roots. And based on this, and based on what our initial solution was, your y1 is going to be e to the r1t, and your y2 is equal to e to the r2t. So these are your two solutions that you get based on the roots. Okay, so with that in mind, these two solutions, y1 and y2, y1 and y2 will form if you will form a fundamental set. And recall, we just talked about this. A fundamental set of solutions is, you can check that with a Wronskian. So if you really want to check it, you can check it using the Wronskian. But just know that with y1 and y2 as the fundamental set, this will give you a fundamental set. So you don't really need to apply the Wronskian. These two will be, y1 and y2 will be distinct roots. So you don't have to worry about that. And so as a result, the general solution will be a linear combination of y1 and y2. So the general solution will look something like c1 y1 plus c2 y2. And so you can rewrite that as c1 and then y1 is e to the r1t and c2 e to the r2t, like so. And that is your general solution for when you have two distinct roots. Okay, this is case A. Now we look at case B, and case B is a little bit more complicated, and this is why I'm going to use the Wronskian, or this is why I showed you the Wronskian before, because it will we're going to have to use the Wronskian kind of like a pseudo proof in order to do what I'm about to do now, because it's a bit jank, to be honest. But it doesn't matter, because the intuition is more important than the proof. So this is for the intuition. So b squared minus 4ac equals 0. This is case B. So in case B, we know that b squared minus 4ac is 0. And we know what r is, right? R is this thing. R is this thing. So if b squared minus 4ac is 0, then r is just minus b over 2a, right? Because this term, the second term right here, is just 0. I can use a pointer. This is just 0. So that's really convenient. So then r is just minus b over 2a. And that's great. But that means that you have one solution, which is e to the rt. But the thing is, in order to have a general solution, remember what we said about linear combinations? In order to have a general solution, kind of like here, you need to have two vectors where those two vectors are not scalar multiples of each other, and they're not the zero vector. And so this is a bit of a problem, because we're only really given one solution. So we need to find a second solution, and it cannot just be some scalar multiple. Like y2 cannot just be a e to the rt, such that a is an element of the reals. This will not work, because if you plug this into the Wronskian, you will get a 0, and that means that won't form a fundamental set of solutions, and well, that's not what you want. So we have to guess and check, and we have to guess and check and find a y2, and basically the y2 comes down to e to the rt. And the way to prove this to you, that these two form a fundamental set of solutions, is by using the Wronskian. So if we use the Wronskian on this, we can see for ourselves that y1 and y2 do indeed make up a fundamental set of solutions, and therefore we can have a general solution that is a linear combination of y1 and y2. So let's do that. So y1 prime is r e to the rt, and y2 prime is e to the rt plus t e to the rt times r. So here, r t e to the rt. And let me bring back the definition of Wronskian right here. Okay, so definition of Wronskian right there. So as you can see, we can just plug these values in for the Wronskian. So y1, y2, and then y1 is e to the rt, t e to the rt, r e to the rt, e to the rt plus rt e to the rt. Okay? And then, so we can rewrite this as y1 e to the rt, e to the rt plus rt e to the rt minus y1 prime, which is r e to the rt, y2, which is t e to the rt. This does not equal 0. And if we simplify this, if we bring the e's out, then that will be e2 to the rt 1 plus rt minus minus rt e to the 2rt does not equal 0. Okay, and then just because of my OCD, I need to bring these down. Give me a sec. Okay, and then all right, so then what we can do is this e to the 2rt, we can bring that all out, and then 1 plus rt minus rt does not equal 0, and so then those two can cancel, and therefore we can say e to the 2rt does not equal 0, because like we said before with an exponential function, even though we don't know what the value of rt is, whether it's positive or negative, it will never be 0, right? This will never be 0. So we know that. And so therefore, this is good. Therefore, y1 and y2 form a fundamental set of solutions. There you go. So based on that, we now know that y1 and y2 form a fundamental set of solutions. That's great. And so we've proved, we now know what y1 and y2 would be for case B. And so we could now write the general solution of case B. So general, and I should change my color for this, general solution, and that general solution would be something like y equals c1 y1 plus c2 y2. So therefore y1 equals c1 y1, and y1 is e to the rt, and c2, and then y2, and y2 is te to the rt, like so. And so that is your general solution for case B, when you have b squared minus 40c is equivalent to 0. Okay, and then And then for KC, we have this b squared minus 4ac is less than 0, and this is going to give two complex roots. All right, now let's talk about KC. So KC was b squared minus 4ac is less than 0. This is going to give you complex roots. Okay? And but before we look into that, you have to know a few things. So you have to recall that Z, I should probably write this in a new color. Recall that Z is equal to X plus I, Y, and then Z is an element of C. C is the complex set of numbers, and X and Y are elements of the real set. And also remember that I squared is equal to -1. And then also know the Euler's formula. So the Euler's formula is e to the it equals cosine t plus I sine t, such that t is an element of the real set. And so that is what you need to know right now. And so our root that we initially wrote was r is equal to minus b plus minus b squared minus 4ac over 2a. Well, we know that b squared minus 4ac is less than 0. So what we can do is we can rewrite this plus minus, and then we can rewrite this as follows. So we can bring out the -1, and we can say 4ac minus b squared. And that way we have the square root of -1, and the square root of -1 is just I. So r equals minus b plus minus I 4ac minus b squared over 2a. So r equals minus b over 2a plus minus I 4ac minus b squared over 2a. And so therefore your r1 equals minus b over 2a plus I 4ac minus b squared over 2a, and your r2 could be minus b over 2a minus I, and then 4ac minus b squared over 2a. That's your r1 and r2. And from here, well, we're gonna have to kind of simplify this in a way. So we're gonna rewrite r as lambda plus minus I mu. And so your r2 is lambda minus I mu, and your r1 is lambda plus I mu. That's your r1 and r2. And so therefore, based on this, what we could say is, what we know that our trial solution was e to the rt, right? So therefore we can replace the r as lambda plus minus I mu t, and we have two different solutions here. And so based on Euler's formula, and if we expand this out, we get lambda t e to the I mu t, and so then that gives you e to the lambda t. And then based on Euler's formula, if we bring this all the way down here, based on Euler's formula, e I mu t becomes cosine of mu t. Whoops, what's happening? Cosine of mu t plus I sine mu t and that is your y. But we still have this I, so we should, our goal is to get rid of this I right here. And so these solutions, your y1 would be, sorry, you would still have this plus minus here. Forgot about that. So that's your y, and so your y1 would be e lambda t cosine mu t plus I sine t, and then the y2 would just be the same thing but with a negative instead of a positive. And so these solutions, you can call them y1 and y2, and they will form a fundamental set of complex valued solutions. And so if I was to write this out, y1 is e lambda t. I'm gonna copy all this actually. So y1 you could write as positive, and then y2 we could write as negative. Okay, so that's y1 and y2. That's great. Now, with that in mind, we are now going to try and assess, like, I'm going to put this in general form. And so what we can say is, we can call this the complex valued linear combination. And the complex valued linear combination looks like y c1 y1 plus c2 y2. But you're probably like, this looks exactly like the same thing that we did before. But what we're going to do is we're going to let c1 and c2, we're going to let them equal a complex value, because since y1 and y2 they're also complex numbers, c1 and c2 should also be complex numbers. So c1 we can write as a1 plus I b1, and c2 we can write as a2 plus I b2. Okay? And so then we can plug everything in, and let's do that. So I'm going to write this in orange. Y c1 is of this value, a1 plus I b1, and then y1 is this, and then plus this c2 right here, and then copy that, and then this is your entirety of your general solution. And I'm going to try and resize this and make it fit. Okay, so that's your general solution right here. Okay, and if we simplify this, basically you're going to come up, you would simplify, I'm not going to go too deep into simplification, but you would have to assign a1 to a2 and b2 to negative b1, and this is just random, but if these are just constants, right? And so it doesn't really matter, I guess. So eventually, long story short, you would end up with, if you have these two simplifications, and again, these two simplifications are a little bit arbitrary, which is why I don't want to go into the derivation, because it seems almost pointless. But this is the basic gist of it. And eventually, you will come down to e lambda t 2a1 cosine mu t plus 2b2 sine mu t, right? And then we can say that 2a1 can equal c1 and 2b2 can equal c2. And so then your y, we can rewrite that e lambda t c1 cosine mu t c2 sine mu t, like so. Okay, and so this is the real punchline here, and this is what we've been working towards. That is very important. That is your general solution. But everything is in the real, but no I, and that's important. So in the general solution, you do not really want the I, and this is what you come up with. So from here we can say the fundamental set is this. Fundamental set is e lambda t cosine mu t e lambda t sine mu t, and that's your fundamental set of solutions. Okay, and so now we've gone through all the cases, and now I'm going to quickly make a small mind map of the three cases, and then we're going to go over like a bunch of examples. And I might have to break this up into 2 videos because the runtime is going to be kind of crazy for this one. But at least you now have a good intuition of where these formulas are coming from. And I'm not just going to give you a mind map. Like that's cruel. Okay? So now let's look at the mind map, or let's just call it map. Okay? So this is going to be the map. And so we're looking at constant coefficient second order linear differential ordinary equations, and this is what we get, right? And now we're going to have three different cases. All right, so we're going to have case A, case B, and case C. And case C. Okay, so case A, B, and C. So with case A, we had b squared minus 4ac was greater than 0. And this is when you had 2 real roots. And then we had case B, which was b squared minus 4ac equals 0. And this was when you had 1 root, right? 1 repeated root, I should say. 1 repeated root. And then we had case C, where b squared minus 4ac was less than 0. And then you had 2 complex roots. Okay, so you have these 3. And so with case A, your general solution looked like the following. So everything I'm going to write in yellow is the general solution. Okay, so your general solution. Your general solution here was when you had y equals c1 e to the r1t plus c2 e to the r2t. And then your fundamental set of solutions was e r1t e r2t, and the r's, I should say, are based on the characteristic equation ar squared br plus c equals 0. Okay, and again we do the same thing. So general solution for the case B, General solution for case B. I should probably make some lines just to make sure that we're given enough space for each. Okay. So the general solution here was y equals c1 e to the rt plus c2 e to the t e to the rt. And then your fundamental set of solutions was as follows, right? It was e to the rt and te to the rt. And then same thing here. So your general solution in case C, or not the same thing, sorry. Your general solution in case C came down to y equals e to the lambda t c1 cosine to the mu t plus c2 sine to the mu t. And yeah, that was it. And so c1 and c2 are parameters, constant parameters. And then your r was in terms of lambda, I, and mu. So that's how it was.
All right. Sorry about that. Someone came to my house. Okay, so like I was saying, r is minus b over 2a plus minus I 4ac minus b squared over 2a. And I'm going to move this arrow just so that you can see better. Okay, that's your r just for case C. Okay, but for case B and case A, the condition is different, right? Because we don't have an I, we don't have a complex number. So for case A and case B, what we got was r equals minus b, I'm going to move this down, minus b over 2a plus minus radical b squared minus 4ac over 2a. That's your r. Okay? And so this was shared by case A and case B. And then also the fundamental set for case C was this. It was e lambda t cosine mu t and e lambda t sine mu t. And I wanted to clarify one more thing. I should have been more clear about the general solution and how I got this, from this. Basically, so these A1 and B1 and A2 and B2, these are just some random constants. And like it doesn't really, you don't really need to worry about how we're getting here. But basically these were the two conditions required. And this was just done so that you were getting just one A1 and one B2. And then this could be rewritten as C1 and C2. So where it's coming from, it doesn't really matter. What matters mainly is how we got the general solution. And this table is very important. So I suggest like you write this down on a sheet of paper and you stick it to a wall or something. And you just look at it every day. And hopefully it'll stick in your head. And so yeah, so this is key. And we're gonna now start doing some examples on all these problems. So let's begin. I have a bunch of problems, so this video might be kind of long. Yeah, I might become like Professor Leonard. Like those guys, his videos are amazing, but they're long. Okay, so we have to solve this initial value problem. Solve this IVP. So y double prime plus 5y prime plus 4y equals 0, and then your IVP is, your fixed condition is y0 equals 1 and y prime 0 equals 0. So first thing that I want you to know is you always want to make the characteristic equation. Okay? So you don't have to do the trial solution every time. You don't have to plug in you don't have to try y equals e to the RT every time. There's a reason why I wrote this table down. It's meant to help you. So first thing we got to do is we got to convert this into the characteristic equation, and I'll highlight this. Okay, so we got to convert this to the characteristic equation. So y double prime plus 5y prime plus 4y just becomes r squared plus 5r plus 4 equals 0. And then we can take the polynomial and we can factor it. So this would be 4 and 1. So then that's r plus 1, r plus 4 equals 0. So then your r equals -1 and r equals -4. And so you're given these there's two roots, and they're two distinct roots. Okay, two distinct roots. And so if you have two distinct roots, guess what? You're going to get two distinct solutions. And those two solutions will be a fundamental set of solutions. So what we can do is, that's equation. What we can do is, we know what R1 and R2 is, right? So R1 is -1, R2 is -4. And I should probably put that in a new color. Okay. Whoops. So there we go. That's R1 and R2. So second thing we do is we form the fundamental set. Form the fundamental set. So how are we going to do that? So in case A, we had all this. So I'm going to just copy the general solution and the fundamental set right here, like so. And I'm going to put it here in a box. There you go. So this is what we're going to work with. Okay? So in order to form the fundamental set, I'm just going to say Fs. Fs is just short for fundamental set. Fs is E R1t, so E minus t, and E to the minus 4t, right? This is your fundamental set. And then from here you make the general solution. I guess the second and third step are a bit redundant. Hopefully when you get very comfortable with this, you won't have to write the fundamental set, but I'm just doing this to drive it in. So the general solution therefore is y equals c1 e to the minus t plus c2 e to the minus 4t. That is your general solution. And now, keep in mind, we are also given these two initial values, these two initial value problems. So let's write that down. So y0 equals 1 and y prime 0 equals 0. So then what you want to do is we can plug this in right now into, so I should be more clear, y is yt, right? So as a result, y0, this is 1, and c1 e to the 0 is just 1, and c2 e to the 0 is also 2. So therefore 1 is equal to c1 plus c2. Okay? And then what you want to do is you want to take the derivative of y prime t. So then that's going to be minus c1t e to the minus t minus 4 c2 e to the minus 4t. And so then now 0 equals minus c1. We just plug it in. So actually I should make a new color. 0 equals minus c1 minus 4c2, right? Because e to the 0 is always just 1. So then that will mean that it is 4c2 equals minus c1. So then c1 equals minus 4c2. So then we plug this into here, and 1 equals c1, and c1 is minus 4, and I'm going to put this in pink, minus 4c2, and then plus c2. And this will be minus 3c2 equals 1. c2 equals minus 1/3. Okay, and then now we need to find c1. c1 is minus 4c2, so c1 is 4/3. Okay, so then now we just plug c1 and c2 back into this general solution that we found up here. So the general solution was yt equals c1 e to the minus t, right? So c1 was negative 1/3 e to the minus t, plus c2, which was 4/3 e to the minus 4t. This is your general, or well, it's your particular solution. Okay, this is your particular solution, and it's particular to the two conditions that were given up here. Particular solution. Okay, that's example 1. The next one I want you to try on your own. So this is the example. So as you can see, like the derivation of the general solution and getting this map was the hard part. But actually solving these equations isn't too bad. Like it's doable, and it's not as bad in my opinion as the derivation and how we get it. In the next video, I'll put up more examples specifically dedicated to the Wronskian. Okay, and so now let's do more examples on second order linear differential equations. So solve the following. Solve the IVP. So this is the IVP. Y prime minus y double prime minus y prime minus 6y equals 0, and y0 equals 3, and your second condition is y prime 0 equals 4. So solve this initial value problem. So first thing we got to do is we got to develop the characteristic equation. And I'm sorry, I should have said, please go ahead, pause this, try it on your own, come back. Okay, I'm hoping you paused it. Okay, you have, right? Okay. All right, so characteristic equation. So characteristic equation would be r squared minus r minus 6 equals 0, minus 1 minus 6. This would be 2 minus 3. So then r would be r minus 3, r plus 2 equals 0, right? And so your two roots, r1 equals 3, and your r2 would equal negative 2. So then again, you have two distinct real roots. Okay? So we have two distinct real roots again. So again, I'm just going to paste, I think it's still on my clipboard. Nice. I'm going to just use this. This was what we derived. And so again, we're going to first find a fundamental set. So the fundamental set is going to be such that your y1 is e to the 3t and your y2 is e to the minus 2t. Okay? And then from here we can create our general solution. And so your general solution looks something like y equals c1 e to the y1 and y1 is 3t, plus c2 y2, and y2 is e to the minus 2t. So then this is your general solution. Now they want us to find the particular solution given these two initial conditions. So what we have to do is first identify, just know that y equals yt, just again to be clear. So when we plug in y0 equals 3 into here, we get 3 equals y0, so c1, and then e to the 0 is just 1, plus c2. This is your first thing that you need. And then because we have two unknowns, so we need two equations, right? So this is your first equation that you have to solve your two unknowns. Your second equation we'll get from taking the derivative of the general solution. So let's do that. Let's take the derivative of the general solution, and that would be 3c1 e to the 3t minus c2 e to the minus 2t. This is your y prime. And then from here, we know that y prime 0 equals 4, right? This initial condition. So 4 equals 3c1 minus 2c2. And so these are your two equations that you need to use to solve. So let's do that. So let me rewrite them here. So your first equation was 3 equals c1 plus c2, and 4 equals 3c1 minus 2c2. So then let's just use this first equation. c1 equals 3 minus c2, because I just moved the c2 to the other side. And then we can just plug that into the second equation right here, and then we can use that and find out what it is. So 3c1, 3 minus c2 minus c2, 9 minus 3c2 minus 2c2 equals 4. And then we subtract 9 from both sides. So that's minus 5 and then minus 5c2. c2, therefore, if we divide both sides by negative 5, comes out to 1. And then we plug this back into this relation, and we find c1 equals 3 minus 1, which is 2. So therefore, your particular solution, is yt equals c1, which is 2, e to the 3t plus c2, which is 1, e to the minus 2t. And this, again, is your particular solution. Okay, good. Now, let's do the next problem. Okay, so example, solve the IVP where the differential equation is y double prime plus 4y prime plus 4y equals 0, and your initial conditions are y minus 1 equals 2 and y prime minus 1 equals 1. So, like always, please go ahead and try this on your own. Okay, I'm hoping you've tried this on your own and you're coming back after succeeding. Okay, so first thing we got to do is we need to write the characteristic equation. So we are given y double prime plus 4y prime plus 4y. So therefore, our characteristic equation must be r squared plus 4r plus 4 equals 0. And so then that means that r plus 2 and r plus 2 equals 0. And so therefore, r plus 2 squared equals 0. So you have one repeated real root, right? R equals minus 2. And so now, again, if we go back, this is case B, where case B was where we had to use the Wronskian to prove to you that the second solution required to span the entirety of the general solutions is TE to the RT. And remember, we got this through guesswork, right? We just, like there was someone a long time ago who had the courage to sit down and just compute Wronskians all day. And he found this. He found that the second solution is TE to the RT. I'm sure there's a very rigorous proof, but I don't know. Sometimes I don't know. I like making fun of math. Okay, so this we need to use case B. This is where we're at. So this is a case B. That's the first thing that should have gone off in your head. And so R equals -2. So then you form your fundamental set. That's the first thing you do, right? Fundamental set. So when you form your fundamental set, the two, your y1 is e to the -2t, and your y2 is t e to the -2t. And these two y's will span your general solution. Okay, so now that we have this, let's create the general solution. So the general solution is y equals c1 e to the c1 y1, and y1 is e to the -2t. So e to the -2t plus c2 t e to the -2t. And now we're also given these two initial conditions right here. Whoops. Hold on. We're given these two initial conditions like so. Okay. So then let's solve this general solution, or let's find a particular solution to the general solution given these two conditions. So first condition is just using y, and recall y equals yt. So 2 equals c1 e to the 2 plus c2 t e to the 2. And then again, we have to take the derivative. So y prime is -2c1 e to the -2t. And then now we have to do a product rule here in the second term, because we have two t's. So first t is c2 e to the -2t plus, or I should say -2 t e, sorry, -2 c2 t e to the -2t. Okay. All right. So now, as you can see, we have this, and this, hold on, this was your first equation. Now we're trying to find the second equation, because we have two variables and we need two unknowns, and we need to find two equations. So -2, I'm going to just bring this e to the -2t out. So e to the actually wait, I'm not going to do that. I'm just going to plug them in, okay? I'm going to plug in y prime of -1 equals 1. So -2 c1 e to the 2 c2 e to the 2 -2 c2, and t was -1, so this becomes a plus e to the 2. All right, and so then we have these two equations, and I'm going to rewrite them down here. All right, so then what I'm going to do is I'm going to isolate to bring the e to the 2 to the other side. So 2, I should be more clear. So 2, I'm going to bring this out, C1, C2t, and then we can bring the e to the 2 to the other side, C1 plus C2t, like so. There you go. And then what we want to do is the same thing here as well. We're going to combine these two, and these two will become C2 e to the 2. And so then we'll have C1 and C2 again, and then we'll have 1 equals minus C1 e to the 2 plus 3c to the 2 e to the 2. And then e to the 2 minus 2c1 plus 3c2 equals 1. And then, where did my t go? Oh, wait a minute. I messed up. Hold on. So when I plugged this in, when I plugged in y minus 1 equals 2, I messed up because I should have had a value for t. This should have just been minus c2 e squared. I apologize for that. Okay, that's your 2. Here, let me rewrite that. Minus e to the 2 minus, there you go. And then this would just become minus c2, like that. Okay, and then, yeah, I'm just checking, sorry about that. Okay, and then 1 over e squared equals minus 2c1 plus 3c2. Okay, and so then you have this one, and then you have this one. And from here you can find c1 and c2, right? So you can solve for one, and you can solve. So here, let's just do it. I kind of wanted to skip it, but whatever. 2e minus 2, and I'm going to put the c to the other side, and this is c1. And then 1 over e squared, so this is the second, minus 2, and then we're going to just dump this entire thing in here, plus 3c2. Okay. This is going to take some space. So all right, so there you go. And then minus 4e to the 2 minus 2c2 plus 3c2 equals 1 over e squared. And then this would be minus 4e squared plus c2, 1 over e squared, and then you add plus 4 e squared over e squared plus 4 e squared. This would be 5 over e squared equals c2. And then your c1, there's always a relation that you come up with. Your c1 is this. So then we can just use that, like so. And then 2e squared plus 5e squared equals 7e squared equals c1. So this is the value of your c1, which is great. And now we can plug that into the general solution to give us the particular solution. So I apologize for all this mess. It's kind of crowded, and it's making me claustrophobic in a way. But anyways, so this is a general solution like so, and we're just going to plug in the values of c1 and c2 to give us the particular solution. So this is the general solution again. And so now the particular solution will look like this. Y equals c1. C1 is e, 7e squared, e to the minus 2t, and then 5e squared te to the minus 2t. And that's how you get the particular solution for this annoying equation. This was a bit of a pain, but we did it. Not bad at all. Okay, let's keep going. Let's keep going. I'm going to do one more problem on case B, and then I'll go to case C, where we look at complex roots. Okay? So let's do one more example on case B. So again, example. Solve the initial value problem. Solve the initial value problem of y double prime plus 2y prime plus y equals 0, y0 equals 3, and y prime 0 equals 2. So, like always, please go ahead and pause the video and see if you can solve this on your own. Okay, I'm assuming you've solved it. I'm assuming you've succeeded. And now we're going to do the problem. First thing we got to do is we got to write the characteristic equation. Whoops. Characteristic equation. And so the characteristic equation is r squared plus 2r plus 1 equals 0. So 2, 1, 1, 1. So r plus 1 squared is r squared plus 2r plus 1. And so r equals -1. This therefore is case B, right? This is one repeated real root. And I never actually went into this, why I call it repeated. You have squared, right? So you have r plus 1 and r plus 1 times r plus 1. So then therefore you're getting r equals -1 twice, right? So that's why. So then r equals -1. Again, this is case B, so I'm just going to, my clipboard got messed up, so I gotta go up here, steal this. This is for case B. So for case B, where am I? There I am. Okay, so for case B, this is what we need. That was weird. Okay, case B. So let's find the fundamental set. The fundamental set is e to the -1t, so e to the minus t, and t e to the minus t. Okay, and then your general solution is y c1 y1, and y1 is e to the minus t, plus c2 y2, and y2 is t to the e to the power of minus t. Okay, and now this is your general solution, and your initial value problem was this. Okay, this was your initial value problem. So then let's recall that y equals yt. So then 3 equals c1, and e to the 0 is just 1, plus c2, and then we have t equals 0. So then c1 literally just equals 3, which is great. And then now we know that yt is 3e to the minus t, c2 t e to the minus t. And so the derivative y prime t equals minus 3e to the minus t, and then we do a product rule here, so c2 e to the minus t plus c2 t e to the minus t minus 1, and this minus 1 I'm just going to write here. Okay, that's your y prime. Now we do 2 equals minus 3 e to the 0, which is 1, and then c2 e to the 0, which is again 1, and then and this is t times t, so then this becomes 0, and so this term cancels and becomes 0. So then therefore c2 equals plus 3 on both sides, c2 equals 5. So therefore your particular solution is this: y equals c1, so c1 is 3, e to the minus t plus c2, which is 5, t e to the minus et. This is your particular solution. That's your answer. Okay, now let's do, let me find, there we go. So now let's do some KC problems. So KC problems are when we have the complex root. So when you have b squared minus 4ac being less than 0. So like before, I'm sorry, like I've been cutting corners. Like the strategy I have here for finding the polynomial, I've done so many polynomials that like I know I have a rough sense of when and when not to get when you can combine it. Basically, all I'm doing here, this is my strategy. So all I'm doing here is this number and this number, I'm just analyzing these two numbers, so b and c. And so whatever two numbers I find here have to sum up to 2, and they have to multiply to each other and become this value. So 1 plus 1 is 2, so that's good. And the product is 1, so 1 times 1 is 1, and so that's why this also works. Ideally you should be using r equals minus b plus minus b squared minus 4ac over 2a, but if you know how to solve it using a nicer way like this, and I'm hoping you do, then you can. But if you can't, then please use that quadratic formula. That quadratic formula is beautiful, and it should be used whenever possible. Okay, so now let us begin doing, with that being said, let us begin doing some annoying complex roots. And I'm just trying to see how many examples I have. I have 1, 2, 3, 4. Okay, I have 4 examples. So let me do the first one. You guys just watch. So first example for complex roots: y prime minus 2y prime plus 5y equals 0, and you want to find the general solution. So then we find the general solution of this. Right, so same thing, we take the characteristic equation. Let me make this IE. So first thing we do is the characteristic equation. So with the characteristic equation, you have r squared minus 2r plus 5 equals 0. And I'm going to try and do it again. So again, this is just Raghav's way of doing it. So this has to be the sum. This has to be the product. And I can't think of anything that products to 5 but sums to -2. So that can't work. So automatically then you know most likely that this could be a complex root. So let me first do the b squared minus 4ac test. So b squared minus 4ac. B squared is -2, or b is -2, so -2 squared minus 4a is 1, c is 5. So 4 minus 20 is less than 0. Therefore, complex root. Okay, and this is a complex root. So now this is a case C, right? So therefore, if we go back up, all the way up into our map, then we can copy this, all of that. Okay, and so oops, let me get the box around it. Give me a sec. Okay, so there you go. That's your box. And now, so let's. Oh wait, this is. Whoops, this is the wrong location. I apologize. This is the right location. Okay. So now, let's do this example. We know that this is going to be a complex root because b squared minus 4ac is less than 0. And so now what we have to do is we have to get r, and we have to figure out r in terms of lambda and mu. So let me write this out. R equals lambda plus minus I mu. And what that means is mu has the value of minus b over 2a plus minus I 4ac minus b squared over 2a. Okay, so now we have to plug it into this form. So minus b is 2, and that's 2 over 2, so because a is just 1, I 4ac minus b squared. So 4ac was 20, like we said here. So 20 minus 4, and then 2a, which is a is just 1, so then that's just 2. So then therefore r is equivalent to 1 plus minus I. 20 minus 4 is 16. Square root of 16 is 4 over 2. 1 plus minus I, 1 plus minus 2i. That is your r. Okay? So now that you've found your r, that's great, because now we can get the fundamental set. So 2 fundamental set. So we have E again, so this is lambda, and this is I, and this is mu. Okay, so lambda is 1. So e to the t cosine, mu is 2, e to the t sine 2t, and that is your fundamental set of solutions. So this is your y1, and this is your y2. And then you have to form the general solution. The general solution is y equals c1 y1 plus c2 y2. So y equals c1 e to the t cosine 2t plus c2 e to the t sine 2t. Okay, that's your general solution. And there you go, that's the answer. I was looking for an initial value problem, but that's all you got. So there you go. This is it. And now, actually, just for time, because I think this video is going to be very long, let's do one more hard example, and then let's call it quits. But basically, I'm hoping by now you've caught on. So first, I really apologize for this. I should have been more clear. Like in all these equations, I was just doing the sum and product way. You could do it this way and find the root, but you could also use this formula, the quadratic formula right here. I should have been better at that, but whatever. I'll write a comment down below or something. Okay, so we now know what the general. Okay, what am I doing? Let's do another problem. Okay, let's do another problem. So, example. Example, solve the initial value problem y double prime plus 4y prime plus 13y equals 0, and then your initial values are y0 equals 5 and y prime 0 equals -4. Like always, please go ahead and try this, and I'm going to give you a hint. This is a case C, so I'm going to bring this down, and oh no, come on. Okay, good. So this is case C. All right. So please go ahead, try this on your own. All right, I'm hoping you've tried it. Now let's go ahead and solve it. So first thing we always do is we write the characteristic equation. Okay, so r squared plus 4r plus 13 equals 0. And I'm going to do it the Rogov way, sum and product. I can't think of anything that can be two numbers that can be multiplied and be given the product 13, and two numbers that sum to 4. So therefore we have to do b squared minus 4ac is less than 0. So b squared is 16 because 4 squared is 16, and then 4, 1, 13 is less than 0. So 16 minus 26 times 2, which is something, I don't know, 26 times 2, 12, 1, 4, 5, 52. 52 is less, yes, it is less than 0. Okay, so therefore this is a complex root. Okay, so then now we have to find r, and I'm just going to come up here and I'm going to copy all this. So in order to solve, we need to find r. So r is minus b, so minus 4 over 2 plus minus I 4ac minus b squared. So 4ac, well, we know 4ac is 52 and b squared is 16 over 2a, a is just 1. So minus 2 plus minus I, and then this becomes minus 30. All right, well, that I is already here. Yeah, so just 36. 36 over 2. So square root of 36 is 6. 6 over 2 is 3. So minus 2 plus minus 3i is equal to r. And r is lambda plus minus mu I. Okay? So now we have to create the fundamental set. Let's do that. Fundamental set. So the fundamental set is e to the lambda t, and so lambda is minus 2t cosine 3t, and then this is your y1, and your y2 is e to the minus 2t sine of 3t. Okay, that's your fundamental set. And now the general solution is y equals c1 y1 plus c2 y2. All right? And so now y equals c1. c1 is some constant, and y2 is e to the minus 2t cosine 3t plus I should have put a t up here, c2 e to the minus 2t sine 3t. That's your y. All right, and now your two initial value problems were up here, like so. And I made it easy because t is 0 for both. And I'm going to switch this color to purple and make it bigger. Okay, so now we're in the home stretch, guys, almost there. So now remember, y equals yt. Okay, and so now what we got to do is we got to first we just got to plug in this thing. So 5 equals c1 e to the minus 2t, e to the 0 basically, and that's just 1, and cosine of 0 plus c2 e to the 0 again, which is 1, sine of 0. Sine of 0 is 1 because if we look at the unit circle, then we're looking at 0, and 0 is 1 and 0, and let me remind you, the x is represented as cosine theta and y is represented as sine theta. So therefore sine 0 has the value of 0, so this is just 0, and so then cosine 0 has the value of 1. So c1 equals 5. Okay, and now we can plug that into what we know so far into the general solution. So the general solution can be rewritten as y equals 5e to the minus 2t cosine 3t plus c2 e to the minus 2t sine 3t. Okay, and I might just put this on the next page because we're running out of space. So let's put that on the new page like so. And y prime 0, I'm just going to copy this, is negative 4. So let's take the derivative and recall, as always, y equals yt. Okay, and so let's take the derivative of y prime t. So this is going to be minus 10 e to the minus 2t, and this is going to be done by product rule. Cosine 3t plus 5 e to the minus 2t minus sine 3t times 3, and this is just one term, and then we have the next term, which is c2. So this is again going to be done by product rule. So then you have a minus sign here, so minus 2c2 e to the minus 2t sine 3t plus c2 e to the minus 2t 3 cosine 3t. Okay, that is disgusting. Why? So let's combine stuff. So we can combine this and this. So minus 10 e to the minus 2t plus c2 e to the minus 2t, and this is cosine 3t plus negative 15 e to the minus 2t minus 2 c2 e to the minus 2t sine 3t. And so then I'm going to plug this in, and I'm going to use purple because I can. 4 equals minus 10, and then this is just e to the 0, which is 1, plus c2 cosine 3t, and then minus 15 minus 2c2, and then 3t, t is 0, so there you go, and then sine of 0 again. Sine of 0, like we mentioned before, is just 0, and then cosine of 0 is 1. So 4 equals minus 10 plus c2. We add 10 to both sides. c2 equals 14. So therefore, your particular solution, your particular solution is y equals 5e to the minus 2t cosine 3t plus 14 e to the minus 2t sine 3t. And that is your answer. Yeah, that was a long video. If you've made it this far, you're a real G. Yeah, this was an important concept. Please let me know what I could have done better. I feel like there were like a few areas that I knew I could have done better. But yeah, I won't keep you too long. Goodbye.